Hello everyone, and welcome to part 4 of our chapter 2 material. And this video is primarily going to be example problems for the chapter 4 material, specifically with the kinematic equations that we've come up with. And so I've already written out the 5 kinematic equations which we produced in previous videos, along with the missing column, which is the term that is missing from each of the equations. And what we want to do is we want to not only work out a couple of example problems with these equations, but we also want to apply them to a falling object, or what the book would call a falling body problem. But before we get into the falling body problem, I do want to go back and make a comment on one of the things that was mentioned in the previous video, which was the rule of 3, which said that given any 3 of the 5 kinematic values, we could solve for the other 2. And that is going to be true in almost all cases. However, there is one exception to that rule of 3. And I'm going to give you that example right now. Let's consider that you are traveling in your car with a constant velocity of 5 meters per second. And because your velocity is constant, that means that regardless of how far we travel or for how long we travel, the initial velocity of 5 meters per second is going to equal any of the other velocity values that we choose to measure, hence the reason why the velocity is constant. Now, if our velocity is constant, then our definition of acceleration, which says the difference in the velocities divided by the difference in times, is going to have to equal 0, because our final and our initial velocity at any point during the journey of this vehicle is 5 minus 5 over whatever time frame. Doesn't really matter at this point, because 5 minus 5 is going to be 0. And so what we have is a case scenario where if our velocity is constant, then we must have an acceleration that is equal to 0, and vice versa. If we have 0 acceleration for our object, then that object must be traveling with a constant velocity. And so we can take this information and we can plug it into our 5 kinematic variables, or 5 kinematic terms, and we have initial and final velocity both of 5 meters per second, and we have an acceleration of 0 meters per second squared. So those are 3 values, which means that we should be able to solve for the other 2. We should be able to solve for the displacement and the time. But consider what information we really have. All we know is that we have a car or a truck that's traveling at a constant velocity, hence 0 acceleration. So if you're traveling down the road at a constant speed, how far do you go? If you're traveling down the road at a constant speed, how long does it take you? And if those questions sound confusing, that's good, because to take this information and plug it into a kinematic equation, we're not going to have a whole lot of success. Let's just try. let's take the 3 pieces of information that we have and let's try to solve for the displacement. So this means we're looking for the equation that leaves out the time entirely, and that is the bottom equation right there. We have v final squared equals v initial squared plus 2a delta x. Now if I start plugging in the values that we have into this equation, the final velocity was 5, the initial velocity was 5, we have 2 times the acceleration, which was 0, times the unknown displacement value. Now the first thing that we should note is that anything times 0 is going to be 0, and so this whole final term in the back is going to equal 0, but we still achieve a true statement. We have 25 equals 25. So there's nothing wrong with the mathematics here. But in introducing the value of the acceleration, we actually lost the displacement term. Well, let's see what happens if we rearrange the equation before we plug the numbers in. We're trying to solve for delta x. So let's see what happens when we rearrange everything. If we rearrange the equation, delta x would have to equal v final squared minus v initial squared all over 2 times the acceleration. And now we can try plugging the numbers in. V final, 5 squared, v initial, also 5 squared, divided by 2 times 0. And we end up with 0 over 0. And some people will look at that and they'll say, well, that equals 0. Other people would look at that and they would say it equals infinity. Because one of the concepts that we can take away from certain math classes is that if you divide by something that is infinitely small, you have to get something that is infinitely big. But if you multiply by something that is infinitely small, then you have to get something that is infinitely small. So where are we? What is our answer? Well, turns out our answer is going to be somewhere between 0 and infinity. And I know that doesn't really help, because this means that technically all answers could work for this. And this is why we take the ratio of 0 divided by 0, or in fact anything divided by 0, and we say that it's undefined. So if you have ever tried to divide by 0 with your calculator, which I know we all have, your calculator will usually give you either an error statement or it may even say undefined. So it's not that the answer does not exist, but we don't have enough information presently to figure out what that answer is. Well, so let's try the time then. Let's try solving for the time, which means we're going to leave out the displacement value in the math. And the equation that leaves out the displacement is this one. But again, you can see what's going to happen. The term that I'm going to try to solve for is currently being multiplied by the acceleration, which is 0. So we'll end up with 0 for that last term, and again we have a true statement. The initial and the final velocities both equal 5, but we don't have a way of actually solving for the time. So this is the one exception to the rule of 3. Technically we were given 3 pieces of information, but we cannot solve for the other 2. Now one way that we can get around this restriction is we can say, well, do we really have 3 distinct pieces of information, or do we just have two? Because our velocity, which is constant, technically that's only one value. And our acceleration, which we have a number for, that's one value, which means altogether we only have two pieces of information. I'm going to have to get either the displacement or the time as a third value if I expect to do any kinematics with this. So if we go back to our picture of the car that's traveling at a constant 5 meters per second with zero acceleration, let's ask the question, how long would it take for the car to travel 200 meters? So this is something that we can actually do now. We will insert a value of 200 meters, and we're trying to find the time that this takes to happen. So I definitely want to make sure that whatever equation I use involves the time. But whatever equation I use, I want to make sure that it only uses one or the other of the velocity terms. In other words, I can go back up and I can pick from any of these kinematic equations, but whatever I pick, I want to make sure that it's either leaving out the initial velocity or the final velocity. So I'm really limited to using one of these two equations if I want to figure out what the end result is. So I think what I'll do is I'll use this equation right here. So delta x equals v naught t plus 1/2 at squared. And we're trying to find the time. So we're going to, let's see here. If we were following along with my 10 steps for success on our homework problems, the first thing we should do here is we should rearrange the equation to solve for time. Unfortunately, this equation is quadratic with respect to time. And so if I wanted to rearrange the equation to solve for t, I would have to set up the solution for a quadratic equation. So what I'm going to do is I'm going to be a bit lenient on the 10-step problem-solving process, and I will allow you to insert one numerical value into this expression. And the one that I'm hoping you will pick is this one right here, the acceleration. Whenever you have a zero to work with in any of your math, use it. And if we do that, this whole second term, even though it does include a time value, that whole second term is going to go to 0. And all that we're left with now is delta x equals v naught t, where v naught is actually the constant velocity v. So I'll divide each side by v, and we get our time. Our displacement was 200 meters. Our velocity was 5 meters per second. And so we plug all of this in, and we should get 40 seconds for the total time. And that brings us to the end of the first example problem with these kinematic equations. So again, this rule of 3, we have to have 3 unique kinematic values. We cannot use the situation where we have constant velocity and 0 acceleration. Technically, it does not work with the rule of 3. All right, so now I want to go ahead and we'll move on to the kinematic example problems involving gravity. And so we'll have some falling objects. And I'll actually bring us down here. So what we're going to do, we're going to find ourselves a cliff somewhere. And we'll drop a rock off of the edge of the cliff. We will release the rock from rest. And if the cliff is 30 meters tall, so 30 meters from the ground up to the point where we have released the rock, I would like to know how long that rock is falling through the air, and I would like to know what its final velocity is when it hits the ground. So of those two values, the other kinematic values are initial velocity, acceleration, and displacement. In this case, we are working with the vertical direction. And so instead of using delta x, I'm going to use delta y, because y is traditionally used for the vertical. So these should be the three values that we already know. These should be the values that are given to us. And we're very tempted to go ahead and just put in some numbers there, but I want to remind you that when it comes to these physics problems, we also need to have a frame of reference. And it is that frame of reference that tells us what direction is positive, what direction is negative, and from there, those positive and negative directions are going to affect the sign notation of these kinematic values. So what I want to do is I want to draw the directions that these individual kinematic values are pointing in. Our displacement, we're starting at the top of the cliff and we're traveling down. So our displacement is down 30 meters. Our initial velocity is 0, so technically it doesn't really have a direction. But we do know that when we get to the bottom of the cliff, the moment that the rock impacts the ground, that final velocity is also pointing down. The final thing that we know is that as an acceleration, gravity points down. And so there's a lot of stuff in this problem. All of it is oriented down. It might make our life a whole lot easier if we chose a reference frame that kept all of our terms positive. There's nothing wrong with having negative terms in our kinematics, but having those extra negative signs and having to keep track of them in the math, it's doable, but if you don't have to have those minus signs in there, why bother? So I'm going to go ahead and choose down as the positive direction in this problem. We're going to work through the kinematics, get our final answers, and then just to prove the point, we'll come back and we'll do this exact same problem again, but we'll flip that reference frame so that up is the positive direction, and we'll see just how little of an effect that actually has. But we do need a reference frame designated so that we know what the positive direction is. Now that we have that, we can start filling in the values. The displacement, delta y, we know that this rock is going to displace 30 meters, but now we also know what direction it is displacing. It is displacing in the positive direction. and that's because we've designated down as the positive direction. So everything inside our kinematic box of terms here is going to have to agree with the choice of reference frame that we have. The acceleration is also pointing down in the positive direction, which means that we have a positive value of gravity. So what is gravity? Well, gravity has a value of 9.8 meters per second squared. The initial velocity was 0. And now we're good to go. We have our 3 values. We can now solve for the other 2. Now, some people look at this and they say, well, isn't gravity supposed to be negative? And I say the answer to that is no. Gravity can be negative, but it can also be positive. So how do you know? And the answer is right there. What direction is the acceleration due to gravity pointing in? And in this case, it is pointing in the positive direction. So our acceleration is a positive g. It is a positive 9.8. So let's figure out the time and the final velocity. Now, I do have some people that will make an honest mistake, and they'll say, oh, well, once the rock hits the ground, it's no longer moving, so the final velocity is 0. But that is after the fact. Yes, once the rock hits the ground, it will come to a stop, and the velocity will be 0. But a better way of thinking of this is, instead of calling this the final velocity, maybe we can call this the velocity at impact. That's what we really mean by final velocity. How fast is the rock traveling when it strikes the ground? So there are 2 equations that I need. I need one equation that leaves out the time, and I need one equation that leaves out the final velocity. The equation that leaves out the time is the last one on our list. And remember that we're working in the vertical direction now, so anywhere where we had an x in any of our terms, I'm now just going to replace them with a y to match up with the vertical direction that we happen to be traveling. And because gravity is a constant, we are justified in using the same kinematic equations that we came up with. All right, that's the equation we're going to use. Our next step is to rearrange the equation to solve for the value that we're trying to solve, which is going to be the final velocity. And the only thing that I have to do to get the final velocity is take a square root of each side. So when I do that, and we can't take the square root of each individual term, it has to be the square root of both sides entirely. And the consequence of a square root is that you get a positive negative solution out of that. So there's 2 possible solutions here. Which one do we want? Well, that brings us back to the reference frame. Which way should that final velocity be traveling? It should be traveling down. What direction is down? Well, down is the positive direction as defined by our reference frame. So we want the positive solution. We're going to go ahead and plug in all our values. The initial 0, 2 times a, which is the positive 9.8, times the displacement, positive 30. And now is where we can see the importance of having the proper sign notation on our values. And the the importance of having the reference frame, because now that I have a square root, I cannot evaluate the square root of a negative compound. So all the stuff that ends up underneath that root has to produce a positive value. And in our case, we do. We have, sorry, I had 9.81 there. That was just how I learned the value of gravity. But we have 2 times gravity times 30. And then we need to take a square root of that value, which gives us a final impact velocity of approximately 24.26 meters per second. So this is how fast the rock is going to be traveling when it strikes the ground. 24.26. Now we need the time. As mentioned in a previous video, we probably don't want to use calculated material unless we're absolutely sure that we have the right answer. But we can check our work a little bit later after we figure out what the value of the time is. But that's okay, because we still have the 3 pieces of given information that we can use to solve for the time. That means we're going to go back up to our list of kinematic equations, and we will pick the equation that is leaving out the final velocity, and that is the third one here. And so that equation says that, and again, we have a delta x in the equation, but we're going to replace all of the x's with y's. So delta y equals v initial t plus 1/2 at squared. We are solving for the time. Our 10-step problem-solving process says take the equation, rearrange it to solve for the time, but again, this is a quadratic in terms of time. So let's go back and see if any of the given values would be of any help to us. Like, oh, there's a 0. We could insert the initial velocity of 0 into the expression. And if we do that, the whole first term drops out, and we're left with delta y equals 1/2 at squared. And for this, we can actually solve for t without having to set up a quadratic solution. If we rearrange everything for time, we would need to multiply each side by 2, divide by the acceleration, and then take a square root. And again, the consequence of a square root is that there is a positive-negative solution. However, in this class, things don't happen before the fact. We cannot have the rock strike the ground before we release it. And that is what that negative solution would imply. That negative sign would say that the rock actually hits the ground before we even let go, and that is just physically not possible. So we will always have positive time solutions in this class. If you want to talk about negative time solutions, then you can come back and you can take a course in relativity. But now we have a similar situation here where we have a root, and we cannot take the square root of a negative compound. And that means that everything that goes into this expression has to produce a positive result. and back to, get rid of this window, there we go. So we go back to our reference frame yet again. We see the importance of having the proper sign notation on all of these values, and when I plug in the values of acceleration and displacement, those are both positives, and so I'm going to get a ratio which is positive, and that can be evaluated through the root. So 2 and 30 makes 60 divided by 9.8, and we need a square root of that, which is approximately 2.47 seconds. So 2.47 seconds. All right, our chart of kinematic values is full, which means we're done with the problem, except as good physics students, we want to make sure that our answers are correct. So we're going to take the two answers that we got, we're going to plug them into one of the kinematic equations that we have not yet used in this system. And let's see here, I think we can probably go with the first equation. We haven't used that one yet. We can plug our two values into that equation. Along with the initial velocity and the acceleration. So it looks like the term that we're going to throw out for right now is the displacement. But if we can put these four values into that equation and get a true statement, then we'll be pretty confident in the fact that these two answers are correct. So here we go. Final velocity 24.26 equals initial velocity 0 plus acceleration 9.81 times time 2.47 seconds. And I say that we have to have a true statement, which means our equality has to be satisfied. But keep in mind that as we've gone through the mathematics and the calculations, we may have had a little bit of rounding error. And so what I'm getting is that 24.23 should equal, or excuse me, 24.26 should equal 24.2307. So here's where we see the error from any rounding that was made as we were solving for these values. But these values are within the acceptable range of error for Wiley Plus, and so I would accept this as being a true statement that confirms that both of our answers are correct. Now again, if you're not sure, you can go back and you can take another of the kinematic equations, something else that we haven't used, maybe this fourth equation right here. Delta x equals half the sum of the velocities times time. So let's try that one. Delta x equals half the sum of the velocities times the time. And we want to see if that gives us a true statement. So in this case, we're using delta x is 30, half of the final velocity, 24.26, plus the initial velocity 0, times the time of 2.47 seconds. So does that give us a true statement? And again, if there's a little bit of variation in the answers, if it's within, I would say, 1 decimal value, we're probably doing a pretty good job with our physics. So as I put this into my calculator, I get that 30 equals 29.9611, which I'm pretty certain would round up to 30, and so both of these answers would suggest that the values that we solved for the time and the velocity are acceptable. Okay, well, as promised, we said that we were going to take this same problem and we were going to do it again, but we would flip the reference frame over. And if we do that, if we flip the reference frame over, well, there's going to be all kinds of interesting things that happen. And so what I'm going to do, I'm going to just start from scratch here with listing out all of the values. But we'll keep in mind that the answers that we got for the final velocity, our final velocity should be 24.26 meters per second, and the time should be 2.47 seconds. Now, physically, should those answers change just because I chose to flip over this arbitrary label of a reference frame? And the answer is, of course not. Things that fall should still fall the same way, regardless of what we consider to be up or down. But we want to prove this to ourselves. We want to make sure that the math is not misleading us in any way. We'll still have the same cliff of a height 30 meters. Gravity will still have the same value of 9.8 meters per second squared. And our initial velocity will still be 0. So we'll go ahead and start filling things in now. We have 0 for the initial velocity. But the acceleration is still pointing down, but down is now the negative direction with respect to our reference frame. So our acceleration is no longer g, it is negative g. And now is where we can actually write out that negative 9.8 that some people might have been thinking about. Because in a lot of classes, it's just assumed gravity is negative 9.8, and that's because it's pointing down, but it has everything to do with the reference frame. Now, later on, we're going to run into a number of, let's just call them algebraic shuffling in the equations. And if I have an equation like, let's say A equals B plus G, and I subtract G from each side. Okay, algebraically, those are the same expressions, but now that I've moved G over to the other side of the expression, what is the value of G? And the answer, at least the answer that has always made the most sense to me, is that the sign on G is the sign on the number. So right here, we have G equals 9.81. In this case, the sign on G is positive. If the sign on G is the sign on the number, then that means we have a positive 9.8. Well, what's our acceleration here? Well, our acceleration is G in the negative direction. hence the negative g. So what is the value of negative g? And again, the sign on g is the sign on the number. And technically, these two expressions are equivalent. I can just as easily factor out the minus sign on either side of this expression and get this one right here. So how does that work over here? Well, if we replace g with 9.81, well, what happens when you move that over to the other side? Well, you have negative 9.81. So algebraically, we need to keep an eye on not only the sign notation for gravity, but how the initial sign notation is defined, and that's going to come from our choice of reference frame. So the sign on g is the sign on the number, but whether that sign is positive or negative comes from our choice of reference frame. Now we have one more value that we have to incorporate, and that is the value of the displacement. So how far does this rock displace as it falls? And everybody would agree that that is 30 meters, but in what direction? We are displacing down. Down is the negative direction in terms of our reference frame. And so our displacement must be negative 30 meters. Those are the three given values. We can now use those to solve for the other two unknowns. And again, we should be able to duplicate these values. Well, we had plenty of luck using this equation in solving for the final velocity value. So let's try using that again. The only thing that we had to do here was we had to take a square root of each side. So we'll do that again. We get v final equals square root v initial plus 2a delta y. And there was the consequence of having two possible roots. Well, now, do I want the positive solution or the negative solution for my final velocity? And again, right here we can see that the final velocity should be pointing down. That is now the negative direction with respect to our reference frame. And so I want the negative answer. Negative root, and we can start plugging in our numbers now. Initial velocity was 0. 2 times negative 9.8 times negative 30. Now there's a whole lot of negative signs all over the place here, so we need to be careful in keeping track of these. But the first thing that I want you to note is inside of the root I have the product of two negatives, which is going to result in a positive. So I am taking the root of a positive that will produce a real solution. If you find yourself taking the square root of a negative, stop, go back, and find out where your error is. Because if you try to take the square root of a negative, you're going to end up with an imaginary solution. And imaginary solutions do not work in the physical world, which is what physics is describing. So we put all this information into our calculator, and well, we get exactly the same answer as what we got before. The only difference is the minus sign out front because of our choice of reference frame. And that's the only difference. This does not change the fact that the velocity was still oriented down. All it changes is that we chose our our positive direction to be up instead of down. So should we expect the time to be any different? And the answer is no. Should we expect the sign on the time to change the way it did with the velocity? And again, the answer should be no. We cannot have things happen before the fact. The time has to be positive. So now it's our job to figure out how are we going to solve for that. How are we going to solve for the time? 6 meters per second. Well, this is a calculated value, so I'd rather not use that, but I can use my givens along with an equation that involves the time. And that equation, well, that's the same equation that we used the last time through. If we try to rearrange this to solve for time, it's not going to work out very well. So we'll go ahead and sneak in the value of the initial velocity, which was 0. And well, we're right back to the solution that we had the last time. But again, we have to be careful with the values that end up underneath that root. We have a negative 30 and a negative 9.8. But that's okay because 2 negatives makes a positive. And we will once again end up with a solution of time equal to 2.47. So whether the reference frame was up or down, it didn't really affect the outcome of the physics. It just affected how we needed to label the values inside of the mathematics themselves. And if we want to take a moment to double check our solutions to make sure that these are correct, we can do that. Let's see, which equation can we try? V final equals V initial plus AT. That was one of the equations that we used to check our work. So does 24.96 negative equal 0 plus negative 9.8 times 2.47? And if we crunch the numbers, again, we're going to see that within a couple of decimal places, we do in fact get the same answer on either side. All right, so there we have a couple of example problems with the kinematics. In closing, I would like to take a moment to do just a couple more example problems, not so much with the kinematics, but with the functions for position, velocity, acceleration, because we were able to produce all of these kinematic equations using the calculus. And we said that for each of those, we need to have some kind of function that we can actually use the calculus on. So what I'm going to do is I'm just going to throw out a random expression. Maybe this expression describes the changing position of a particle with respect to time in meters. And so I would like to know what is the velocity of this particle. And our definition of velocity is change in position with respect to time. And so if I were to take the derivative of this function, it would produce a function for the changing velocity. And we know the easy way of taking derivatives. We can come through here and we can say this is going to be 6t minus 5. 7 doesn't have a a variable attached to it. The derivative of a constant is 0. And so there's my time-dependent function for the velocity. If we take one more derivative, then we will get a function for the acceleration with respect to time. Well, if I take the derivative with respect to time, the only thing I get out of this is a 6. There are no more t's, and so this tells me that whatever this particle is, it's accelerating at a constant rate, and so the kinematics that we've learned about would be justified in describing the motion of this particle. Well, is it possible to have a particle that does not have a constant acceleration? And that answer is yes, you can. I'm going to put in a different function over here. We'll say that the changing position can be described by this function. So completely different from what we have over there on the left, but we can come through here with our calculus and we can produce a function for the velocity followed by a function for the acceleration. And because we still have t's present in the function, that means that the acceleration is not constant. But does that mean that we can't use kinematics on this particle? We can, but it would be more difficult because not having that constant acceleration would mean that we would have to be a bit more stringent in the mathematics that we do. But this is not to say that we can't have a particle changing its acceleration. We're just not prepared to tackle problems like that at this point in the class. So we're not going to attempt any kinematics with those types of equations, but that doesn't mean that we cannot evaluate these functions at given time values. So even though I X'd this out, maybe I want to know what is the acceleration of this particle at t equals 2 seconds. In that case, we would plug in a 2 for the time. 2 cubed is 8. 8 times 80 would be 640. So there's the acceleration at 2 seconds. Pretty straightforward. Likewise, everything over here we should be able to evaluate at any given time. If I wanted to know the position of this particle at time t equals 0, then I would plug in a 0 for the time. And in evaluating that, all that would be left is the 7. If I wanted to know what the velocity was at time t equals 0, I plug in a 0 for all the time values and I would get a -5. As for the acceleration function, well, it's a constant. Even though I have it written as a time-dependent function, all of my time dependencies have dropped out in the calculus and I now have a constant acceleration. Well, what else can you do with these functions? Well, remember the average acceleration? Well, we can use these to help us find the average velocity and average acceleration of a given particle. But to do that, we need to know what the initial and final values are associated with the corresponding times. So right now I just have initial and final values, but maybe I want to know what is the average velocity of this particle between t equals 1 and t equals 3. So our first time value is 1 second, our second time value is 3 seconds. those are the values that are going to go into our equation. So we have a time interval of 3 minus 1, or 2 seconds. But then we have to evaluate our position function at those given times. So what is our position when time equals 3 seconds? In that case, we have 3 times 3 squared minus 5 times 3 plus 7. So what do we have here? We have 27 minus 15 plus 7. 34 minus 15, so that is, oh, my brain's starting to shut down on me. I'm going to have to get my calculator out for this. 27 minus 15 plus 7. There we go. 19. 19 meters. And what is the position at x equals 1? So 3 times 1 squared minus 5 times 1 plus 7. So now that all of these are 1s, we have 3 minus 5, which is negative 2, plus 7, which is going to get us back up to 5. And now we can plug those values in to our average velocity expression. 19 minus 5 over 2. That gives us 14 over 2, or 7 meters per second. That is the average velocity between those two time values. Now, is that the same as the velocity at 3 seconds? To answer that question, we come to the velocity equation that we made, which says that 6 times the time minus 5. 18 minus 5, what is that? Well, that's 13 meters per second. That's quite a bit of a difference between what we have up there. Average acceleration between, we'll go ahead and use these times again. So what's the average acceleration between those times? Well, I would need to know the velocity at 3 seconds, which is right there. We already solved for it, 13. And the velocity at 1 second. So 6 minus 5 is 1. And then we would have to divide that by the time interval, which is still 2 seconds. So we have 12 over 2, which is 6 meters per second squared, which should not be surprising because our acceleration is a constant. And so if you were to ask yourself, what is the average value of a constant? Well, it is the constant. And that's exactly what we just proved here using this method. Now there are some other interesting things that you can do with this. Now that we have expressions for position, velocity, acceleration, we can ask very specific questions like, at what time will the velocity equal 0? And so we can take our velocity expression, which is 6t minus 5, and we can actually force the expression to equal 0. And then we can solve for the time required for this to be a true statement. So to do that, I would have to add 5 to each side and then divide by 6, and there's my answer. That is the time where the velocity will equal 0. And if you plug that value back in to the expression, you'll get 0 for your answer. Okay, well, if that's the time where the particle comes to a stop, where is it? Where is the particle when the velocity is equal to 0? Well, we just found out at what time that occurs. So let's plug that time value into our position expression. And that will tell us where our particle needs to be. We have 3t squared, which will be 3 times 5/6 squared minus 5 times t plus 7. And so this is not going to come out to be a very nice answer, but that's what we have our calculators for. We have 5/6 squared times 3 minus 5 times 5/6 plus 7, and assuming I haven't made any errors with my calculator entry, I'm getting approximately 4.92 meters. So that is the physical location where this particle comes to a stop. Now, why would the particle come to a stop? Well, this would imply that the particle was moving in one direction, slowed down, momentarily stopped, and then started traveling in the other direction. And that is a possibility. Other things that we can figure out would be, let's see here, is there any kind of maximum or minimum values? So back in calculus, whenever we were asked this, if there were max or min values, the answer to that would be to take the derivative of your function, set it equal to 0, and solve. Well, that's exactly what we did with the velocity. We took the position expression, which was 3t squared minus 5t plus 7. We took the derivative of that and set it to 0, but the derivative was the velocity expression. And we solved for the time of 5/6. And plugging that value back in, well, surprise, surprise, this is actually the maximum value, or the maximum position value that this particle will achieve during its displacement, at least in the positive direction. As time goes by, the particle may start traveling in the negative direction. It may even end up turning around again, depending on how the function in the mathematics plays out. But now that we've seen those examples, along with the examples of the kinematics, we are going to bring Chapter 2 to an end. There are still plenty of example problems that we could do with this material, but we're going to continue the discussion of kinematics when we get to Chapter 4. In Chapter 4, we're going to start doing these kinematic problems in 2D and 3D space, and so we'll be more than ready to tackle those case scenarios when we get to them. So, closing out of Chapter 2, give that homework a shot and contact me if you run into any issues.